This video will talk about the center of the Milky Way galaxy and some of the observations, some of the conclusions, and some of this material has been seen in other videos. Um, but I'd like to call your attention to a nice movie of the zooming in on the center of the Milky Way galaxy. It's available from YouTube. I'm not going to play it here, but it's made by the European Southern Observatory, and it gives a nice zooming in, first in visible light, and then the dust becomes too thick for visible light to penetrate. Then infrared light is used to see closer to the center of the Milky Way galaxy. And then in the last segment of the video, there's a gas cloud that is seen to be falling towards a black hole at the center of the Milky Way galaxy. So it's not falling directly in, but it's headed that way. So it's an interesting video. I'll let you look at that on your own. So Sagittarius, the constellation of Sagittarius, it's a summer constellation for observers in the northern hemisphere. The center of the Milky Way galaxy is not too far from Sagittarius, so X marks the spot over here. And this is in a dusty area. We can see starlight that's not been obscured by dust right in here, but gives you a little location of where the center of the Milky Way galaxy is. So if you're taking this course in the winter, you'd have to get up in the early morning to see Sagittarius, and possibly you'll just wait till July to look where Sagittarius is. The teapot is the asterism for the constellation of Sagittarius. So handle the teapot, the top of the teapot, the spout of the teapot here, and going off the spout of the teapot, curving up a little bit, we find the center of the Milky Way galaxy. You can point that out to your friends sometime. Visible light, here's a photograph showing this region again in between the constellation of Sagittarius and the constellation of Scorpius over here. Lots of dust in evidence here. We're looking in the plane of the Milky Way galaxy, and these black clouds are dust that's obscuring the light, causing extinction of the light from the more distant stars behind them. When we look in different wavelengths, here we have the Spitzer telescope information looking in the infrared. Here we have Hubble and visible light, and here the Chandra X-ray telescope looking at X-ray emissions. The center of our galaxy is active and emitting X-rays, and these can be combined into a composite photograph. Students in my class should look at the large poster in the hallway of our science building on first floor, and you'll see these composite photographs of the center of our Milky Way galaxy. And again, X-ray information, very energetic processes happening at the center of the Milky Way galaxy. We'll get into that. Gas and dust, the yellow being kind of the Hubble telescope infrared view, and then the more reddish, the Spitzer telescope, further into the infrared, sees better through the dust. But putting this into composite gives a nice composite piece of information. So, motion of stars with the infrared telescope. Astronomers have observed stars in motion around the center of the Milky Way galaxy. From the size of the orbit and from the speed of the stars in the orbit, astronomers have calculated that there's a supermassive black hole at the center of the Milky Way galaxy. Again, all the mass that's in a black hole is creating this large gravitational effect and holds light in, but the effect of gravity gets out of a black hole. So we have it's affecting the stars. These stars are not inside the event horizon by any means. They're outside. As astronomers look at this infrared information of the positions of stars, they can also look with information of X-rays and energetic processes generating energy, emissions from the center of our Milky Way galaxy. The interesting thing about these emissions, or one useful thing, is that these emissions are variable. They come and go with several minutes of time, 15-20 minutes of time. And that implies to astronomers that all this mass that's at the center of the Milky Way galaxy, several million times of the mass of the sun, all this mass has to be within a size of roughly the Earth's orbit to get the time variations to to take place in 15-20 minutes, the object can be no larger than 15 or 20 light minutes in size, and that's roughly the diameter of the Earth's orbit. So you're packing in millions of masses of the sun into the diameter of the Earth's orbit. It's too massive to be a star. It's a black hole. That's our interpretation. Gravity gets out of that black hole and has an effect on the orbits of the stars. But we have a situation here of black hole being discovered in our galaxy, and we'll talk about this in other galaxies as well. So 4 million solar masses would be an estimate of how much mass is in there. The variation in the brightness of the X-rays and in the radio information say that this mass has to be packed in to something about the size of the Earth's orbit. Black hole fits that description. So you ought to be writing down some questions and bringing those to your instructor about the center of the Milky Way galaxy. Again, we have to use infrared light. Radio really is best to penetrate the galaxy gas and dust and allow us to observe the center of the Milky Way galaxy and see these stars moving at high speed, telling us that there's a great source of gravity here, large source of gravity, and variations in the radio and X-ray signals, and the time variation tells us that that's a small object that's creating this high gravity. So there we are for Milky Way center. Brief little discussion of what we have there. Keep reading, keep asking questions. That's where we're going to end.